everyone, and welcome to English 1 at the University of Crete. I'm Noni Rizopoulou, and in this session we're going to explore how computers store, access, and represent information, that is, the very foundation of the digital world. Think about it. When you send a message, watch a video, or play a game, where does all this information actually reside? Is it floating in the air? Or is it hidden somewhere inside your device? Today, we'll follow that story, from bits and bytes to memory, magnetic and optical storage, and input-output devices, and discover how data, logic, and representation shape the way computers think and interact with us. By the end of this session, you'll understand not just how computers store information, but also how that information is organized, retrieved, and transformed into the images, videos, and sounds we use every day. Have you ever wondered how computers actually store information? Inside every computer, all the data we see, text, images, even music, is reduced to just two symbols, zeros and ones. These symbols are called bits, short for binary digits. On their own, bits don't mean much. They're simply patterns of zeros and ones. But depending on the application, those same patterns can represent anything, from a letter on your screen to a frame of video or a note in a song. It's often helpful to imagine that a zero means false and a one means true. This simple true-false logic forms the foundation of all digital systems. Through combinations of bits, computers can perform calculations, make decisions, and store complex information. When grouped together, bits can represent numbers, letters, colors, or even sound waves. For example, a single photo on your phone contains millions of bits, each encoding tiny details like color and brightness. No matter how complex the data seems at its core, it's all patterns of zeros and ones, organized, stored, and processed at incredible speed. Once we understand that bits represent true or false values, the next step is learning how we can manipulate those values. This is where Boolean operations come in, named after the mathematician George Boole, who lived in the 1800s. Boole's work laid the foundation for the logical systems that make computers work today. In regular algebra, we describe numeric relations, equations, and quantities. But in Boolean algebra, we describe logical relations, how truth values interact. Instead of adding or subtracting numbers, Boolean algebra combines true and false statements using simple logical rules. There are three main Boolean operations: AND, OR, and NOT. AND means both conditions must be true for the result to be true. OR means either condition can be true. NOT simply reverses a value, turning true into false and false into true. These simple operations are the building blocks of all digital circuits and computer logic. To visualize how these operations work, we can use a truth table. A truth table lists all possible input combinations and shows the corresponding output. It's a clear way to see the logical behavior of a circuit or system, whether that's a basic switch or a complex microprocessor. In computing, not all operations work the same way. Some act on just one value, while others combine two. When one operation acts on only one input, it's called a unary operation. When it acts on two inputs, it's called a binary operation. A unary operation takes a single input and performs an action, for example, flipping a bit from 0 to 1 or applying a NOT operation. A binary operation, on the other hand, combines two bits or values, like AND, or addition in arithmetic. These binary operations form the backbone of most computational processes. When we describe operations, we often use two key terms, the operator and the operand. The operator is the symbol that represents the action, for example, a plus sign or a logical AND. The operand is the object that action is applied to, in other words, the data itself. For example, in the expression A plus 1, plus is the operator. A and B are the operands. Together, they define the operation being performed. One of the most fundamental logical operations is the logical conjunction, also known as the AND operation. It works on two logical values, or in computer terms, 2 bits. The conjunction produces a result of true only when both of the inputs are true. Let's think of it like this. If both conditions must happen at the same time, for example, it's sunny and warm, then the result is true only when both parts are true. If even one part is false, the whole statement becomes false. That's the logic behind the AND operation. We can visualize this with a simple truth table. It lists all possible input combinations and their results. As you can see, the output is 1, true, only when both inputs are 1. Another essential logical operation is the logical disjunction, more commonly known as the OR operation. Like conjunction, it works on two logical values or 2 bits, but this time it produces a result of true if at least one of its inputs is true. Think of it like this. If we say it's sunny or warm, the statement is true if either part is true or even if both are true. It only becomes false when both parts are false. That's the principle behind the OR operation. Let's look at the truth table for the OR operation. As you can see, the output is 1, true, whenever at least one input is 1. So the logical disjunction or OR operation produces a true result when either or both inputs are true. It's how computers represent situations where multiple conditions can lead to the same outcome, a key idea in programming and digital logic. Now let us look at logical negation, also called the NOT operation. Unlike AND and OR, this operation works on just one logical value or a single bit. The negation simply reverses the value. If the input is true, the output becomes false. If the input is false, the output becomes true. Think of it like a light switch that flips the opposite of whatever it's given. If the input says true, NOT turns it to false. If the input says false, NOT turns it to true. It's a simple but fundamental building block in both digital circuits and programming logic. Here's a truth table for the NOT operation. As you can see, the output is always the opposite of the input. Next, we have the exclusive disjunction, commonly known as the XOR operation. Like AND and OR, XOR works on two logical values or 2 bits. But here's the key difference. XOR produces true only if exactly one of the inputs is true, not both. Think of it like a special switch. If only one input is true, output is true. If both inputs are true, output is false. If neither input is true, output is false. XOR is useful in situations where you want a signal or condition to be true only when the inputs differ. Here's the truth table for XOR. As you can see, the output is true only when the inputs are different. Now that we understand Boolean operations, let's see how they are implemented in hardware. In electronics, the physical devices that perform Boolean operations are called logic gates. They are the building blocks of computers. Logic gates can be built using different technologies: mechanical systems like gears, relays, optical devices. Modern computers use small electronic circuits where the digits 0 and 1 are represented by different voltage levels. To make them easier to understand, gates are often shown in diagrams. Inputs enter on one side, the operation is performed inside the gate, and the output exits on the other side. This makes it simple to design and visualize complex circuits. Inside a computer, information is rarely just a single bit. Instead, computers work with long strings of bits, which we often call bit streams. These streams can be hundreds or even thousands of bits long. For humans, bit streams are hard to read and interpret. Writing them down or transcribing them is tedious and prone to errors. This is why we often need a simpler, more readable way to represent them. Hexadecimal notation, or hex, is a base 16 numbering system using 16 symbols instead of the 10 we use in decimal. It's convenient because bit patterns in computers are usually multiples of 4, and each hexadecimal digit can represent exactly 4 bits, half a byte. Using hexadecimal makes bit streams much easier to read and write. It's widely used by programmers and computer designers to simplify coding, debugging, and system documentation. So instead of writing out long strings of zeros and ones, we can represent them compactly and accurately using hex. To store data, a computer uses a large collection of circuits, each capable of holding a single bit. These bits are organized in a way that makes them easier to manage and access. This is what we call main memory. Main memory is divided into small units called memory cells. A typical memory cell can store 8 bits, which we call a byte. So each cell usually has the capacity to store 1 byte of information. Even though computers don't have a physical left or right, we often think of the bits within a cell as being arranged in a row. Each cell is assigned a unique address which acts like the cell's name. We can imagine the memory cells lined up in a single row, numbered sequentially starting from 0. Computers need to communicate with the outside world, whether it's a human user or another system. This is done through input-output devices, or I/O devices for short. Input devices allow the computer to receive data. For example, a keyboard or a mouse lets the user provide information or commands to the system. The computer then converts these physical actions into signals it can process. Output devices allow the computer to send data. Monitors, printers, and speakers take information from the computer and present it in a form humans can understand. Essentially, output devices translate digital signals into something meaningful in the real world. Interestingly, whether a device is input or output depends on your perspective. A keyboard is an input device for the computer, but it is an output device for the human user because it converts human actions into signals. Similarly, a monitor outputs information from the computer, but from the human perspective, it receives that data as input and displays it in a comprehensible way. Input-output devices can be divided into storage devices and non-storage devices, depending on whether they can retain information. Non-storage devices allow communication between the computer and the outside world, but they cannot store data. A good example is a printer. While it produces a permanent record on paper, this record does not reside inside the computer unless it is manually typed or scanned back in. Storage devices, on the other hand, retain information for later retrieval. Their contents are non-volatile, meaning the data remains even when the computer is turned off. Storage devices can be magnetic, like hard drives, or optical, like CDs and DVDs. Let's take a closer look at magnetic storage devices. These devices use magnetization to store bits of data. In a magnetic storage devices, each spot on the storage medium can be either magnetized or not. A magnetized spot represents a 1, a non-magnetized spot represents a 0. This is how computers can represent and retain digital information using magnetic patterns. Magnetic storage is non-volatile, which means the data remains even when the power is turned off. It typically uses read-write heads to access information on magnetically coded surfaces. These heads detect or change the magnetic state of each spot, allowing reading and writing of data. A magnetic disk is a thin, spinning disk coated with a magnetic layer used to store data. Data is written and read by read-write heads positioned above and below the disk. As the disk spins, the read-write heads move along circular paths called tracks on the upper or lower surfaces of the disk. Each track holds a sequence of bits representing the stored information. Often, a magnetic disk system consists of multiple disks stacked on a common spindle called platters. Read-write heads are carefully positioned to slip between the platters, allowing simultaneous access to multiple surfaces. On a magnetic disk, each spinning disk surface is divided into tracks, circular paths where data is stored. However, a single track can hold more data than we usually want to access at once. To manage this, tracks are divided into smaller arcs called sectors, each one storing a continuous string of bits. Every sector on a disk contains the same number of bits. A sector represents the smallest storage unit that can be accessed in a single operation, making it a convenient unit for reading and writing data. Tracks and sectors are not physical features of the disk. Instead, they are magnetically marked during a process called formatting or initializing the disk. This is typically done by the manufacturer before the disk is ready for use. The performance of a disk depends on 3 key factors: rotational speed, which is how fast the disk spins, seek time, which is the time it takes for the read-write head to reach the correct track, and transfer time, which is the time needed to move data from the disk to main memory. Another form of magnetic storage is the magnetic tape. In these systems, data is recorded on a thin plastic tape coated with magnetic material and wound on a reel for storage. To read or write data, the tape is loaded into a tape drive, a device that can move the tape forward and backward under computer control. The drive handles reading, writing, and rewinding the tape as needed. A major drawback of magnetic tape is slow access times. Moving to the specific position on the tape can take a long time because the tape must be wound through the reels to reach the desired location. This makes tape much slower than magnetic discs, where sectors can be accessed almost immediately. Optical storage devices use light, typically lasers, to store and retrieve the data. The most familiar example of optical storage is the compact disc or CD. A CD is about 12 centimeters in diameter and has a reflective surface covered with a clear protective layer. Data is recorded by creating tiny variations on the reflective surface, which a laser reads as the disc spins. These variations encode digital information in the form of bits. DVDs use multiple semi-transparent layers, each acting as a separate surface that a precisely focused laser can read. This allows DVDs to store several gigabytes of data, enough to hold an entire motion picture. Video is stored as a series of images called frames, displayed in sequence to create the illusion of motion. Each frame is converted into bit patterns and then stored on the disc, allowing movies to be retrieved and played back digitally. Finally, when representing images digitally, there are two popular techniques, bitmap and vector. Each method encodes images in a different way and has its own disadvantages and limitations. The bitmap method represents an image as a collection of dots called pixels, which is short for picture elements. Each pixel stores color or intensity information. One limitation of bitmap images is rescaling. Enlarging a bitmap simply makes the pixels bigger, which can result in a grainy or pixelated appearance. The vector method represents images as a set of lines and curves defined by mathematical equations. The device then renders the image based on these definitions. This approach allows images to be rescaled freely without losing quality, making vector graphics ideal for logos, illustrations, and designs that need flexible sizing.